I hope this is working. Can somebody let me know if the microphone's working? I think it should be. I can see the little bar moving on the screen here. Yes, it is. Excellent. Brilliant. Right. So what we're going to do, what I thought I'd do is do something a little bit different with these live streams. And I thought we'd go and do, it's working. Brilliant. You can hear. Excellent. Excellent. Brilliant. Okay. So what I thought I would do is do something a little bit different with these live streams. These live lessons. So what I thought I'd do is do some year 2 content, because I know we've been doing some year 1 content before. But I thought just to try and kind of, well, strange times, isn't it? But what I thought I'd try and do is try and bridge that gap between year 1 and year 2 and kind of introduce you to some year 2 content as well. So I've decided to pick something which is quite similar to year 1 content. I know some people, when I asked for suggestions, they were asking about enthalpy changes and looking at that. So I thought I'd just blend year 2 enthalpy changes, like enthalpy reactions, etc., and link it in with the year 2, with some of the year 2 content as well. So I've done it in a way where this lesson I'm going to go through the content. I'm going to try and cover the whole lot. It should take about an hour roughly, depending on, that's what I plan to do. So hopefully I should be able to do that. And then what I plan to do on Thursday, if you can join us on the Thursday one, then I've got some questions, and the questions are actually in the link. If you click on in the description box, there's a link with all the questions. I've done the questions already, but I'll go through the questions in Thursday's live lesson instead of today. So today, somebody's just put, is this revision or does it start from scratch? I'm going to assume that you don't know this, so I'm going to start right from the basics, strip it back, and try and go through it as much as I can and link it with year 1. So I'm assuming that you haven't done this. That's the approach I'm going to take on this. But I'm going to try and bridge it from stuff that you've done in year 1 and link it in with year 2 stuff. So hopefully that should work. So the idea is go through the content, try and remember as much as you can from this. Have a go at the questions, which are in the link in the description box, like I say, and we'll go through the answers to them questions in Thursday's live lesson. So that's the plan. I think the best way to do this is I'm going to go through the content on here, but I want to try and keep this interactive as well, rather than just me just talking at you and showing you stuff on here. I think it's going to be a little bit easier, you interacting with the stuff here as well. So if you do have any questions, put them in the chat box, and I'll be able to pick it up and I'll kind of go through some information there. Okay. Right, I think somebody said, I also noticed somebody said, is this hard? Is this topic hard? I think somebody's put that. I can't see it. Somebody's asked. Laura Ladybird has said, is this topic hard? I hope not. It's not. It's about in the middle. It's not probably one of the most difficult ones. There's some tricky bits here because we've got Gibbs free energy, etc. Just before start as well, just one extra thing. This is quite generic. I've tried to pick topics which are generic, whichever exam board you do. I know if anybody who studies salters, you won't need to know. About the Gibbs free. I don't think that's in there as well. And if you do Edexcel, you need to know a little bit extra. But I'll add a little bit more in here. But this video is designed to kind of cope with all. With most of the stuff in here, the vast majority, I've tried to keep as generic as possible so it'll appeal to everybody, whatever exam board you're doing. Okay. Right, okay, are we good to start? If I put yes in the chat if you're good to start, and I'll just make a start if that's the case. It's a bit cooler today at least. Yes, you are. Brilliant. Excellent. Right, let's make a start then. Right, so everything seems to be working fine. So, fingers crossed this should work. I've squashed myself into the top corner, as you can see. I don't know, I'm pointing the wrong way. As you can see, I've squashed myself in the top corner because all the stuff's going to be in the middle. So that's why I've done that. Okay. Right, cool. Right, so let's make a start. So, okay, so the first thing, what we're going to look at is definitions first. So types of enthalpy change. Now, you need to know these definitions because I'm going to show you something called the Born-Haber cycle, and that's going to use these definitions here. So it is just a lot of, like I say, definitions regarding this. So what I would recommend you do when you go through this, because it'll go onto YouTube as well. After it's gone live, it'll all be available on there. So just go and have a look at the definitions on here as well. So the first definition is a few of these, which is enthalpy of formation. So enthalpy change of formation. You might have seen this in year 1 chemistry. So this is where the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. So you just need to know that this is enthalpy of formation. So it's the formation of 1 mole of substance. Very, very, very important. These are easy marks, dead easy marks. You just need to know the definitions. And when I say easy marks, I mean you get about 2 or 3 marks for just writing a definition. So it's easy marks from that front. Okay, enthalpy of formation. So we need that. Okay, so you would have seen that in year 1 in Hess's cycle. So you would have seen that. There's nothing new there for that one. The next one is lattice enthalpy of formation. You might not have seen this one. This might be quite new for you. Enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions under standard conditions. So what we're saying is we're forming a lattice, a giant ionic structure. Okay, so we're forming that. And we'll form that from ions in the gaseous state. Again, a lot of this will be much better in context. So I'm just going to go through all the definitions here, and then I'm going to put it into context, okay? Right, lattice enthalpy of dissociation is just the opposite of formation. So this topic is going to be a lot about ionic compounds and ionic substances. There's going to be a lot about that in this live lesson. So everything I'm talking about here is about the formation of ionic compounds. So if you remember, ionic compounds are big, giant ionic compounds with ions in there. You've got positive and negative ions, that oppositely charged ions that are attracted to each other. So if you can visualize that giant cubic structure, that's what we're talking about here. So lattice enthalpy of dissociation is the breaking up of that giant structure. Okay, so it's the enthalpy change when 1 mole of a solid ionic compound is dissociated into its gaseous ions under standard conditions. Okay, so you've got the example there. Okay, the next one is lattice, or is the enthalpy change of dissociation. Okay, so this is the enthalpy change when 1 mole of bonds of the same type of molecule in the gaseous state is broken down. So that's F2 gas to 2F gas. Okay, so enthalpy change of dissociation. Okay. It can also be written as atomization as well. So there's 2 ways depending on your exam board. So right, next one is ionization. You would have seen this in year 1. This is the enthalpy change when 1 mole of gaseous ions, they're 1+ ions, are made from 1 mole of gaseous atoms. So we're just removing an electron. So that's the first ionization energy. So that's the removal of 1 electron from an atom, and you're forming a charged ion. Okay. Enthalpy change of atomization. So this is where so it's the enthalpy change when 1 mole of gaseous atoms is made from an element in its standard state. So it's half F2 going to F gas, for example. So that's atomization. Again, a lot of this you'll see it in context in the cycle. So I'm just whizzing through these. Second ionization energy is just the same as the first ionization, except it's the energy required to remove a second electron. So that might be, for example, calcium. You remove 1 electron and then you remove a second one to form Ca2+. Okay. And then electron affinity. This is the enthalpy change when 1 mole of gaseous 1- ions are made from 1 mole of gaseous atoms. So, for example, oxygen gas to O- gas. The state symbols are really important here. And the final one here is the second electron affinity. So this is adding a second electron to something that already has a negative charge already. Okay, so all of these definitions here all fit into a Born-Haber cycle, which we're going to look at. Later. In the next slide actually. The definitions really, it looks a bit. You're probably looking at that thinking, Christ, there's loads and loads of stuff there. How am I supposed to remember that? I think the best way with things like this is just put it into the cycle and see it in context, and then it kind of makes a little bit more sense when you see it. Okay, so I'm gonna. Damn, that's a lot. Yeah, it is a lot. There is a lot there, but trust me, it looks quite scary there. It's a lot better when you see it in a cycle. Okay, and I'll try and explain the cycle there as well. All right. Okay. Right, so let's move on. Let's move on to the cycle. Right, so we're going to look at something called the Born-Haber cycle. Okay, so a Born-Haber cycle is really similar to a Hess's cycle. Okay, it's just a big Hesse cycle. That's all it is. So when you look at this, I don't want you to look at it and think, oh my word, that looks really, really scary. So we're actually going to be looking at breaking down the Hesse cycle. And all of these cycles here are to do with ionic compounds. It looks like a lot of work for making an ionic compound, but that's what you need to have in your head. It's always to do with ionic compounds. So sodium chloride, calcium oxide, for example, potassium chloride, just ionic compounds. So we're forming ions, and then we're working out the energy changes for each of these steps to form the ions, okay? So Born-Haber cycles, they're useful to calculate lattice enthalpies. Okay, so remember, an enthalpy is an energy change per mole, okay? And a lattice enthalpy is the energy required to form a big ionic lattice. So it's basically, we're just working out how much energy it takes to form an ionic compound. That's all it means, okay? But Born-Haber actually goes through a lot of this in detail. So we can't calculate this directly from experiments. So we're going to look at it structured in this particular way, okay? So now, when you're drawing a Born-Haber cycle, I'm going to show you how it's structured here, and it goes in a very specific order. And what I would encourage you to do, if you're obviously, you might not have seen this, and most of you probably won't have seen this at all. Some of you might have done. You might have seen this already if you've done it, if you've moved ahead after year one chemistry. But what I always do is you put your solid compound. In this case, we're going to look at the lattice enthalpy of lithium chloride. Okay, and so what I've done is we've put lithium chloride at the bottom here. So you can see it's LiCl solid. Okay, so lithium chloride solid. And then that goes at the bottom on a big line right at the bottom. That's the base of your Born-Haber. It's always your solid compound at the bottom. Okay, and then what you have is we have our elements here in their standard states. So you might seen elements in the standard states kind of rings a bell from year one chemistry, because it's the enthalpy of formation. Okay, so it's the formation of a substance, 1 mole of a substance, from elements in their standard states. So to make lithium chloride, we need lithium solid, because it's a metal, and we need chlorine gas. We need half Cl2, because we only need 1 chlorine. So that's got to be a gas there. So these are the elements in their standard states. That's how we'd start a Born-Haber cycle. Start with the bottom line, and then the next line on the left-hand side, put the elements in their standard states. Okay, that's how we'd always start it. Right. There's no questions so far, so I assume that's all fine. Right, so this is, like I say, enthalpy of formation. Key thing, exothermic. Okay, all formation, enthalpy of formation is always exothermic. And you'll notice on these diagrams here, any arrows that point down like that are exothermic, because it's negative. It's a negative enthalpy change. So imagine this as like levels, and the higher the level, the higher the energy. So if we're going from a higher level to a lower level, then we're going to release energy because it's exothermic, it's negative. Okay, is everybody following so far? I hope so. I'm going to keep going, but if you're not, then like I say, just put it in the chat and I can go through it again. Okay, so it's always exothermic, it's formation. So the next step. So what we're going to do, let me just give you a little bit of background behind what we're trying to do here with Born-Haber. You think, well, what on earth is this? What we're trying to do is say, right, look, we've got our enthalpy of formation here, so we can form lithium chloride from the elements in the standard states, and it's just a one-step process. So it's lithium solid, half Cl2 gas, okay, and that's one step that is exothermic, okay. But we've always got, like Hesse cycle, we can also make lithium chloride by going an alternative pathway. Now I use an analogy, I live in Morpeth in Northumberland, so there's 2 ways in which I can get to Newcastle, for example. I can get to Newcastle going straight down the A1, okay? That's the direct route, so that's like this route here. That's like going lithium plus half Cl2 to lithium chloride, okay? That's direct to Newcastle. If, though, that road is blocked, or it's busy, as it normally is, then I can go an alternative way, and I can go down the A19. Now, that's a longer route, but I still get to the same location, okay? Born-Haber and Hesse cycle is exactly the same. You've got 2 routes to get to lithium chloride. One route, the direct route, is forming elements in their standard state. So I can go from lithium, half Cl2 to lithium chloride. But let's imagine, okay, I've got that route, I need an alternative route. How else can I make lithium chloride in theory? So this route here, where I'm going now, is showing an alternative method of making lithium chloride. Okay? I hope you're following. Okay, so the first one there, so when I'm going up here, this is the first step to the alternative route to make lithium chloride. So that first step is atomization. So what I'm doing is I'm turning half Cl2 into Cl gas. Okay, so Cl atom. I only need one chlorine, so I have to break that Cl2, I have to break the bond there, and just end up with one chlorine atom. Okay, that's gas there. So this is called enthalpy of atomization of chlorine. This is an endothermic process. I need to put heat energy in to break that bond. Okay. Okay, so he says that in year 11 you've started this as chemistry work. Wow, this is year 2 chemistry, so you're quite a bit ahead if you understand this. Right, so the next thing what I need to do is we then need to try and atomize our lithium as well. So we need to turn lithium solid into lithium gas. So this is the next step. This is atomization of lithium. Again, it's endothermic. I'm turning it from a solid into a gas. I need energy in. Energy needs to go in to turn that into a gas. Okay. The next step is I need to form the ion, okay? Because we're forming an ionic compound, so I need to make ions, don't I? So to make ions, then I need to ionize lithium. So I need to remove an electron from lithium. That's endothermic as well. If you're taking something away from an atom, it isn't going to give it up very easily. So you need to put energy in to remove that electron from lithium, and you form your ion there, and there's your electron. Always write your electron there, okay? Lithium plus Cl plus an electron. It's always in this structure. Get used to this method here, the way it's been laid out here. Get used to that, okay? I've started a yes, not this, yeah. Okay, so oh no, that's fine. This is year 2 stuff. So this is year 2. So you will need to do it if you're doing the full A level. Then you do need to know this. Right, so then we've got our ions there. Now we need to get chlorine into an ion. So we need to add this electron that we've removed from lithium. We need to add that to chlorine. Now we call that electron affinity. So there it is there. Now this is an exothermic process because heat energy is being released when we're adding an electron to chlorine. Remember, chlorine atom's got 7 electrons in the outer shell. It isn't going to put up any form of resistance by accepting that extra electron to form Cl- because it gets a full outer shell. That's a stable molecule, okay, or stable atom. So you can see here that we've got our ions in our gaseous state. So now our last step is to then take these ions here to form our lithium chloride, and this is clearly our enthalpy of formation, lattice enthalpy of formation. Okay, so what we're doing here is we're forming our lithium chloride from ions in the gaseous state, as you can see on there. Okay. So what we're doing is we're forming an alternative route, as you can see. I've got 2 ways in which I can form lithium chloride. I can either go direct from elements in their standard state to form lithium chloride, and that is enthalpy of formation, or I can go indirectly and I can go atomization, ionization, affinity, and then lattice enthalpy of formation. So I've got 2 ways in which I can get to lithium chloride, okay? A bit like 2 ways in which I can get to Newcastle, either A1 or A19. One route's longer than the other, but I still get to the same place, okay? Right, so you can see it's a bit like Hess's cycle, very similar. The total enthalpy change of a reaction is the same no matter which route is taken, okay? It doesn't matter. We're still ending up in the same place. We can either go direct or indirect, okay? Right, I've had no questions so far, so I assume everything's fine. Right, so let's kind of apply this a little bit more. What the exam board will want you to do is they'll want you to calculate or use Born-Haber cycles to calculate enthalpies or enthalpy values in here. And it's very similar to Hess's cycle. So if you're used to Hess's cycle, then this shouldn't be too dissimilar. It's a little bit bigger than normal. So we calculate lattice enthalpies by using the cycle in the same way as Hess's cycle. So we go with the arrow, we keep the sign the same, we go against the arrow and we change the sign, okay? Now you can, if you've got a calculator, if you can grab a hold of a calculator now, then you might be able to join in with this and kind of push the buttons as we're going through it. So if you grab a calculator, that'll be good. Right, so what you'll get in the exam is you'll normally be given, you may even be given the cycle, you may not even need to draw it out, or they may give you half a cycle and you have to complete it. That's why you need to familiarise yourself with the cycle, okay? But in this example, we're taking the cycle that we'd seen in the previous slide and we've brought it here. But this time we've got numbers, okay? So we've got enthalpy of formation of lithium chloride first ionization of lithium, enthalpy of atomization of lithium, enthalpy of atomization of chlorine, and the first electron affinity of chlorine here. So we've got all the enthalpy values that are written down the side there. Okay. So, like I say, if you've got your calculator, what we're going to do is we're going to go through this and work this out. So if you've got your calculators ready. So the first one is the entropy formation. So what we're going to do is we're going to put down all the different values in this cycle here. So we know that this step here is formation, because from our definition, the entropy formation is the formation of a solid ionic compound, 1 mole of solid ionic compound, from elements in their standard states. That's lithium, and that's chlorine in gas. So the value here is minus 409. Okay. So then the next one is the atomization of chlorine. The key thing here, though, is we need to half it. Okay. One of the key mistakes that people make when they do these in the exam is they're not looking at exactly what they've got. You can see here that we've got half Cl2. The data they've given us is the enthalpy of atomization of chlorine is 242. But that's the atomization of 1 mole of chlorine. We only have half a mole here. So you must divide that by 2 to get 121. Don't forget that. Okay. Okay. So the next one is the atomization of lithium, which is 161. So that's fine. The next one is ionization. That's the first ionization energy, which is 519. Okay, so we're ionizing lithium. And then we've got the electron affinity of chlorine, which is minus 364. So it's an exothermic process, remember? Okay. And the bit we want to calculate is the lattice enthalpy of formation. Okay, so that's what we want to calculate there. So we're going to try and work out that value there. So we're going to start from here and end there. Okay, so this is where you need your calculators. If you've got them, if you want to join in, that's fine. But what I'm going to do is I'm going to go through each one of these steps and we're going to work out this number here. And if you could do this, this is really what the exam board are wanting you to do. They're wanting you to get your numbers in there and use the cycle to work out something. So this is the real kind of crux of it, really. This is really what you need to be able to do. Okay, so if you've got your calculators ready, we're going to start here. So we want to work out this value here because we don't know this bit. Now this is a bit like, again, I'm using the analogy of going to Newcastle. I either go direct down the A1 or I can go indirect via the A19. So using that analogy, this is a bit like going from here is like Morpeth, that's where I live, and I'm going to Newcastle, which is down here. So I'm starting from here and I'm ending here. Now I can take this route direct, or I can go indirect and go all the way around the cycle, but still end up in the same place. Okay, so when you want to work anything out, just like Hess's cycle or Born-Haber, what we assume, the bit that you want to work out, we assume that that's like a roadblock, that's closed. We can't go that way. Okay, so we need to start here and we need to go the diversion. We need to go the opposite way around the diagram. Okay, so when we go against the arrow, we change the sign. Okay, and when we go with the arrow, we keep the sign the same. That's the rule. Remember that. Okay, exactly the same as what it is for Hess's cycle. So let's see if we could do it. So we put this in your calculator. So we're going to do, first of all, we're going to look at going against the arrow there. So that's plus 364. Okay, because we're going against the arrow. And then we're going to go against the arrow here. That's minus 519. Okay, literally just put these numbers in. Literally just put them in like that. The next one is minus 161. The next one is minus 121. And because we're going with the arrow here, we keep that the same. So that's minus 409. And you literally put all that in your calculator and it will tell you your answer, which should be minus 846 kilojoules per mole. Okay, so that should be the value in there. That's it, minus 846, spot on. Okay, good. So if you can do this stuff, this is really what they're wanting you to do. They want you to get the cycle, put your numbers in, and use it to work out something. Okay, so you just need to know where you're starting, where you're ending, and you're going the alternative route to what you're trying to find out. Okay, so this is, check the number as well, this is minus 864. That's an exothermic reaction. It should be exothermic because we can see this is a red arrow going down. This is exothermic. If you're getting something that's positive, something's not right. Okay, it must be negative, this value here, because it's an exothermic process. Okay, so it must be, somebody's put, if you go the other way around, it shows 846. I'm not sure what you mean. So if you 846 is if you go against the arrow, okay? But if you follow this method here, this exact method that I've shown you here, you should always get the right answer, always. And a really good way of checking, is if you take that number you've just worked out there, just deposit it in this bit here, okay, next to this arrow, and start anywhere you like on that cycle, anywhere at all. So let's say we're going to start here. Then what we do is we put the number in with the arrow, with the arrow, with the arrow, with the arrow, against the arrow, with the arrow. Put all the numbers in, and you should add up to 0. Always. It should always add up to 0. Following that rule, go against the arrow, we change the sign. You go with the arrow, we keep the sign the same of the number that you're looking at. Okay? Can you do that and just change the sign because it's formation? Yeah, you should. It should be exothermic, yes. So if you get 846, you should put a minus on there. It's always exothermic because it's going down. It's lattice entropy of formation. Okay? Right, okay. So, I hope you're happy with that. We're going to look at more examples, okay? And you'll see on the questions that I've created as well, some exam style questions, then that is one of the first question is a cycle that's already been made up for you. And you just have to answer the questions to do that. It's a very common exam question. So if you're all right with that, you'll be fine. Okay, we're going to do another one. Okay, so this one, we're going to calculate a different part of the cycle this time. Okay, so remember, you're going to go with the arrow, keep the sign the same. We go against the arrow, we change the sign. Okay, we've been given some data here, and we've been given the cycle. So we're using sodium chloride this time. Okay, so we're going to put all the numbers in that we have. Okay, so the first one is entropy of formation. We've got that. That's minus 411. We've got the enthalpy of atomization, again, which is 121. It has to be divided by 2. Remember that. If you don't do that, you'll get a number which doesn't work. Okay, you must divide it by 2 because we've got half Cl2. Okay, in this example here. Now we want to calculate this bit. We want to calculate the atomization of sodium. So it's a different part of the cycle. Okay. We've got the enthalpy of ionization of sodium is 496. Okay. And then we've got electron affinity of chlorine. So we're adding the electron to the chlorine. So it's affinity means to, if you're affinitized with something, it means you're introducing it, you're associating it with it. Okay. So minus 364, it's exothermic. And then the lattice entropy, we've been given this number this time, unlike the other example. This is minus 787. Okay. So get your calculators ready. Okay. We're going to work this out. So where do we start? Where do we end? So have a look at where we start and end. So remember, we're looking to work out this bit. This is the bit we need to calculate. Okay. So remember, this is like the direct route. I want to go this way. So I'm going to start here and I'm going to end here. That's where I'm starting. So I'm starting here, ending here. But imagine that's a roadblock. That's closed. So I need to go an alternative route. I need to start from the start bit and end at the end bit. So let's put them in. There we are. So we're starting from here and ending here. I want to work this bit out as a roadblock, so I need to go the diversion, I need to go the long way around. So I need to go down here, up here, and then back down to where I need to be. Okay, so calculators ready? Okay, let's put the numbers in. So we're going against the arrow with the first one, so that's going to be minus 121. Okay, we're going with the arrow here, so then keep the sign the same, so that's minus 411. Okay, we're going against the arrow here, so we're going to change that to plus 787. Okay, we're going to go against the arrow here, so that's going to be plus 364. Okay, and then we're going to go against the arrow here, which is minus 496. Somebody's quick off the mark, so we just put 123. And then we should have a value. Now it should be, this is an endothermic process. You can see it's a blue arrow. Our number must be positive. Okay, whatever the number is, it's got to be positive. It can't be negative. So the answer is plus 123 kilojoules per mole. So well done, Trash. You got that one right. So that should be 1 plus 123 kilojoules per mole. Okay. So just make sure that you're using the cycle properly. You see, we're just making a start point, going to an end point. It's just taking a diversion. Okay, you've got two routes and where you can go, where you can get to it. Okay, put all your numbers in, put all them numbers in the right place, and follow the rule. Go with the arrow, keep the sign the same, against the arrow, change it. Put all that in, and you should get 0. Okay, it's worth the effort. Just put the number in, see if you get 0. If you do, the likelihood is you would have got it right, and you've probably racked up the best part, depending on the question it's going to ask, it's going to be the best part 5 marks, you know what I mean? So, like I say, there's an example on the question sheet that I've set, and we'll go through the question in Thursday's live lesson. Okay, right, so I'm going to look at another Born-Haber cycle. This one is a little bit tricky, okay, because it's got this funny step in the middle. So what we're going to do is we're going to look at one where we're forming double ions. So we've got magnesium oxide with this one instead, okay? So you can see here, we've got the full cycle here. It's all drawn out for us, so that's fine, brilliant. What we need to be able to do is put the numbers in and work and work some things out here. But what I'm going to do with this, I'm not going to actually put numbers in this one. We're not actually calculating the numbers. What we're going to do is we're going to look at the different features of this particular cycle. So you can see here, we've got magnesium oxide at the bottom, similar feature, and we start with these 2 lines. So it's magnesium and oxygen in their standard states. So that's them there. Notice we have O2 there. It's not half O2, because we need 2 oxygens. The 2 oxygens here. We need that to form, no we don't, we just need 1 oxygen to form your magnesium oxide here, okay? But this will be all formed at the top here, okay? So let's have a look. So we're going to look at second ionization step is the first thing we need to notice here. So this is needed to create the Mg2 plus ion. So remember with the other ones we only had 1 plus, okay? So we only had a sodium plus or potassium plus, whatever, or lithium plus. We only need to ionize once. With magnesium, we need to do it twice. Okay, so we've got to do that twice with that one. Okay, so this one should be this one should be half O2 because you only need 1 oxygen. So I need to get that changed. I'll get all that changed there. Don't worry about that. It's just the actual cycle. Okay, so the second ionization step is the main thing to notice here when we're looking at double ions. Okay, is the one worth more marks? Looks more. Is this one? No, it's probably worth about the same amount. It's just a little bit different. That's all. So you've got second ionization step. Also, we've got the second electron affinity step. Okay, so this is needed to create the O2 minus ion. So now notice here we've got Mg2 plus, your oxygen, okay, and we've got 2 electrons that we've removed. So what we're going to do is we're going to take these 2 electrons and we need to add these to the oxygen. So the first electron affinity step, remember, is forming O minus, as you can see there. Okay, that's only supposed to be 1 oxygen, by the way. Okay, so that's only supposed to be 1 oxygen. That's supposed to be half, and that's 1 oxygen up there. So I'll remove that 2 from all this, so don't get confused with that. Okay, so to add an electron to oxygen, it should be O minus, so that's fine. That's an exothermic process. Okay, remember, oxygen's not going to put up much of a fight to receive an electron because it's gaining that electron to form a full shell. So that's an exothermic process. However, the tricky bit comes in when you're adding a second electron. So we're adding an electron, okay, to something that is already negatively charged. Okay, so this is the second electron affinity. Okay, so because this is already negatively charged, you're trying to add a negative electron to a negatively charged ion, there's going to be some repulsion. Okay, so when they repel, that means you're going to need to put energy in to effectively force that electron, that second electron, onto the negatively charged ion, and that will form O2 minus. Okay, so that's the only step. The second electron affinity is endothermic. Okay, you've got repulsive forces between these 2 negative charges, so that's the only difference. Okay, it looks scarier, but that's the only step. So electron affinity, the first one is always exothermic, and then second, third, etc. moving forward, they're always endothermic. So you've got this kind of funny step in the middle there. Okay. So, like I say, I'm just going to emphasize this again. This should be, and I'll get all this changed as well. This should be half O2, and then it's single oxygen all the way up there. Okay, because you only need 1 oxygen to form magnesium oxide. Okay, right. Okay, so looks fine. I don't think there's anybody stuck on that. Okay, so what we're going to do. Brilliant so far. Excellent. Right. If you're getting the hang of this, this is a big chunk of it done. So Okay, right, that's all we need to know about Born-Haber. So what we're going to do, because we're talking about ionic compounds here, so this works really well when we're assuming that we have perfect ions. Okay, so we have some perfectly ionic substances here. We have ions here forming an ionic compound. So all of this is about ionic compounds. So this one we're going to look at now. You can't see because my camera's in the way, but this is theoretical and experimental lattice enthalpies. Okay, so what the exam board are wanting you to do, and this is the case with all exam boards, okay, this is relevant to all of you, is they're wanting you to be able to calculate, there we are, theoretical or compare theoretical and experimental values, because they actually can be different. Okay, and it depends, now this is really going to kind of blow everything out of the water, it depends how perfectly or purely ionic something is. Right, so you were told, and I'm sure you were told, that you either had covalent, you had ionic, or you had metallic, okay, and that was it. And if it's a metal and a non-metal, you said, right, that's ionic. If it's a metal and a metal, it's metallic bonding, and if it's two non-metals, it's covalent, okay. I'm just going to throw something straight in the water and actually say, in reality, you don't have something that's perfectly ionic. You have a little bit of covalency in there as well. You have two types of bonds. Okay, you can have an ionic compound, in other words, with some covalent character in there. Okay, seems a little bit strange, but it does exist. Okay, so I just want to get that straight there now. Otherwise, you might get confused with what I'm talking about here. So I'm going to say it again. Ionic compounds, some ionic compounds can have some covalent character as well. Okay. So what makes this happen? How do we have this? So theoretical lattice enthalpies can be calculated from data assuming a perfectly ionic model. Okay, so theoretical lattice enthalpies, we can calculate that using the data, but that assumes that it's perfectly ionic. In reality, that isn't quite the case. Okay, so a perfectly ionic model is pretty straightforward. It's just ions that are perfectly spherical. Okay, and the charge is evenly distributed in this sphere. Okay, so we've got something called point charges. Okay, so you can see here we've got a positive charge and we've got a negative charge. So that's, if something's perfectly ionic, it must have that criteria. Okay, it's common to carry out an experiment to work out the lattice enthalpy, only to find the number is different to the theoretical value. Okay, that's always the case in chemistry, isn't it? You always do something practically, it never quite matches what you should get in theory. But this is true. This is what happens. Okay, so this tells us actually the compound being experimented doesn't follow a perfectly ionic model, and it has some covalent character in there. That's a bit sneaky. Okay, so it's got some extra kind of covalent character in there, which does alter it slightly. Okay, so most of the time the positive ion distorts the charge distribution in the negative ion, and we say that the positive ion polarizes the negative ion. So what we get is this bit of distortion here. We don't get this perfect sphere. We actually get a little bit of it looks a little bit like it's trying to share electrons, almost like a covalent bond. Okay. Okay. Could you explain that it is common sense? I'm not quite sure on what you mean. I'll keep going through it. You might pick up on it if I carry on going, if I might answer your question that way. So the more polarization we get, okay, the more covalent character there will be. Okay, so if we've got an ionic compound that has a lot of polarization, we've got a lot of covalent character in there. If we've got something where there's no polarization at all and we've got point spheres, then we have a perfectly ionic substance. Okay, sorted now. Brilliant. Okay, that's fine. Right, okay, so that's the first thing that we need to be aware of, okay, is what we mean by we don't just have perfectly ionic compounds, we have ionic compounds that have some covalent character in it, and we get different figures from practical, some experimental values and theoretical values, okay? Right, so lattice enthalpy values, so these, remember what lattice enthalpy value is on our Born-Haber cycle, so that is the formation of a giant ionic compound. Okay, so that value there tells us how much of a substance is purely ionic. Okay, so how purely ionic it is. So here we've got a data. Okay, you've got data here. You will be given these values. You don't need to remember any of these. So thankfully. So you can see here, it's just to really show you what I mean by this. So we've got loads of different ionic compounds here. So we've got lithium, chloride, bromide, and iodide compounds here, and we've got magnesium, chloride, bromide, and iodide. So we've got a group 1 element and a group 2. Okay, we've got the experimental values, which are there, and you can see that we've got the theoretical values, which are here. Okay, and we've got the difference. What I've done is I've put on the side here the difference in lattice enthalpy. So in other words, how much does the experimental value deviate away from the theoretical value? So the bigger this number is, then the bigger the difference is between the experimental and the theoretical value. Okay, so this is going to be really important because the exam board are going to be wanting you to be able to explain this data, which is exactly what we're going to do here. So in all examples, the experimental value shows a higher lattice enthalpy than the purely ionic theoretical value. So your theoretical value assumes a perfectly ionic substance, okay, no covalent character at all. But in reality, we know that when we do an experiment, we actually work out that there is some covalent character, and that has an impact on the enthalpy value, okay. So this shows that we have some covalent character that's been displayed in our compounds, and this is caused by these larger distortions in the negative ion. Okay, so remember that distortion that we're talking about before? And so this can be seen clearly between your 1+ lithium ion, okay, so there it is there, and a 2+ magnesium, as you can see there. So if we compare the percentages in the two, you can see there the percentage here from a lithium, so 1+ and chlorine, the change is 0.8. But if we take a 2+, keep the chloride the same, you can see the deviation is much greater. So what this is telling us is we have more covalent character in magnesium chloride than we do in lithium chloride. That's what it's telling us there, okay? So, in summary, lithium chloride, in this case, is the most perfectly ionic model. So, lithium and chloride ions, they're point spheres or nigh on, very close, okay? But the bigger the difference in the lattice enthalpy, the more polarization you have, and so therefore you have more covalent character. So the covalency increases the lattice enthalpy, okay? It strengthens it a little bit more, okay? That's all you need to know. Right, okay. So, I don't think there's anybody put any questions on there, so I'll just assume that everything's fine there, and we'll move on. Okay, so that pretty much deals with that side in terms of the lattice enthalpies and looking at the formation of ionic compounds and addressing the fact that some ionic compounds have a little bit of covalent character as well. So we're addressing all of them points there. So now what we're going to shift on to is looking at ionic compounds like sodium chloride, like salt, and looking at how it behaves when we chuck it into water, okay, and we make solutions, we make salt solutions, okay. So this bit is where we're going to look at the enthalpy change of a solution, okay. So let's have a look. So we're looking at another form or another enthalpy form here, and this is called the enthalpy of solution, so delta solution H, okay. So the enthalpy of solution, the enthalpy change of solution, is the enthalpy change when 1 mole of an ionic substance, so that's your solid giant structure, and I've got some diagrams here to show you, is dissolved in the minimum amount of solvent to ensure no further enthalpy change is observed upon further dilution. So all that means is that if you take your solid compound, okay, and we're going to add some solvent to it. So imagine you've got a pile of salt, okay, in a beaker, and you're going to add some water to it in a squeezy bottle, okay. So what you're going to do is you're going to add the minimum amount of water you can get away with to dissolve all of that salt. You don't want any more, so you've got a really saturated solution, okay? So it's just the amount of solvent. That is the enthalpy of solution. There's an energy change happening there when you're dissolving a salt. It may not seem it, but there's an energy change. So we just want to measure how much energy is required to dissolve that, just dissolve it, okay? So I'm going to move myself out of the way here. Okay, there we are. I'm going to put myself over there temporarily. So for a substance to dissolve, okay, there's two things. So substance bonds must break. So we've got to break the substance, and then new bonds are formed between the solvent and the substance. So this is in the context of taking a salt and dissolving it in water. That's all it is. We have to break that salt apart, that giant crystal structure, and then the solvent, which is the water, then has to surround the individual ions and there's energy required there. All right, so let's have a look. Oops, let's get it back onto the screen. Okay, so here's an example. So I've tried to put diagrams in here. I think it helps a lot with this, particularly with this topic anyway. So there's your giant ionic structure there. You've got loads of positive and negatives, okay? And there's our solvent, which is water, okay? So this is a solid, and we're going to add water to it, okay? Oops. Okay, so then what happens is, in theory, now a lot of this is theoretical, okay? So what we have to do is we have to break that structure apart into the individual ions, okay? That's what happens when we dissolve a salt. That's what happens to that structure. So energy is required, is needed to break that structure apart, okay? So that's an endothermic process. Energy is needed to break that apart. So it breaks into the free moving ions, and then what we have is the water then starts to surround these positive and negative ions, okay? And we form a hydrated solution, okay? So the ions are hydrated. So you can see here that energy in this case would be released when because there's now an interaction between the oxygens and the hydrogens here. They're interacting with these ions here. So energy is released. This is an exothermic process, this one here. So you've got an endothermic here, and you've got an exothermic here. So this is effectively what happens when we take a solid salt and a solvent like water, we add it, and this is what you get. This is your salt solution, okay? Right, so most ionic compounds, they do dissolve in polar solvents. So salts, for example, they dissolve quite readily. The reason why is you've got that delta positive hydrogen, okay, is attracted, as you can see there, to the negative ions in your salt, and your delta negative oxygens are attracted to the positive charge, as you can see there. So we get this attraction between these ions, and that's what helps to break it apart, okay? The water molecules surround it. We call this hydration, okay? So this is hydration, and you can look at entropy of hydration. And then the key factor here, the most important factor, is for something to be soluble, okay? The energy here, so the new bonds formed here must be the same strength or greater. So these interactions at this stage here must be greater than what was needed to break up this structure into its ions. If it's not, if it takes more energy to break that up than what's released when the water surrounds these ions, then your solid is unlikely to be soluble at that temperature. Okay, so there's some things that are really soluble and some things that aren't, and obviously temperature plays a part in that as well. Okay, so that's really, really, really important. I assume people are fine with that because I haven't had any comments on there yet. Okay, so hope you're sticking in. This is quite tough. It's not the easiest topic, I must admit. So if you're keeping up, you'll be fine. I think the key thing is to practice this, and like I say, we'll do that on Thursday. I've got questions. You click on the link there. The questions are all sorted, and then you can have a go at the questions, and we'll actually practice this as well. Okay, this is just to kind of give you the content first, and of course you can play this back. You can play this back at any point as well. Okay, right. So let's have a look at calculating the enthalpy change of a solution. So we've looked at how we actually take that salt and we dissolve it in water. So we're just looking at the mechanics of that. So what we're going to do, there's energy changes happening when we dissolve salt. Who thought salt could be so complicated, or dissolving it in water? So enthalpy change of solution can be calculated, okay, from knowing the lattice dissociation enthalpy. So remember that right at the start of this live stream, we looked at the definition of that. So that's when we take a lattice structure and we break it apart. That's lattice dissociation, okay? And the enthalpy of hydration, remember, was obviously forming the hydrated ions, okay? So, yeah, go through it on Thursday. When we go through the answer, we're going to go through. There's questions on the link in here. Go in the description box, click on that. Be able to get a hold of the questions. See if you can have a go at them. It's all based on this. Everything on there is in this video here. And then what we'll do on Thursday is I'll go through the answers. Okay, so to see if you've grasped it. Okay, so what we're going to do here is we're going to use a kind of like a Hess cycle. It's not quite the same, okay, but it's kind of like a Hess cycle to work this out. So what I've got here is I've brought the diagrams back in so you can kind of see what's going on. I think it's really difficult. When you look at cycles like this, you think it just looks like a load of ions and, you know, they all look very similar. So I've tried to bring the pictures back in to show you where it all fits together. So here's your lithium chloride solid. there's your solid compound, okay? That's what it looks like. That's the state that it's in at the moment, okay? And we've got our ions that are aqueous. This is the enthalpy of solution. That's what we just looked at before, remember? So we took our solid, we added water, and we've got our aqueous ions here, okay? So this process here occurs via two steps, remember? It's the breaking down of the structure first, and then it's the attraction of water. So it's like a two-step process. So this is what we're going to look at in our cycle, okay? So the first step here is forming the ions, the gaseous ions, and this is the enthalpy change of dissociation, the lattice enthalpy change. So we're taking that structure there, we're breaking it up into ions in the gaseous state, okay? So that's that first step there. Then what we need to do is we then need to add water, and water will surround them ions, and this is called the enthalpy of hydration, okay, which is that step there. So remember, the enthalpy of hydration is the enthalpy change when 1 mole of aqueous ions is made from 1 mole of gaseous ions. So you can see here, there's your ions there, okay, and we're adding water to it, and this is the hydrated stage. So you can see here, this to this occurs via two steps. You've got the breaking up the ions first, that's endothermic, okay, because heat energy is required to break that up, and then it's the exothermic process here, which is where you get the little attractions between your solvent, your water, and your ions. Okay? I hope you're following so far. Okay, so what we assume, this is the assumption that we do the following. Remember, we break that solid lattice up first, and then we dissolve the gaseous ions in water. That's the assumption that we're making here. Okay? We're going to treat it like a Hess cycle. Okay, so if you've done Hess cycle before, you will have done definitely in year one. So this is kind of a link to year one. You go with the arrow, you keep the sign the same. You go against the arrow, you change the sign. Okay, so you'll be given the data in the exam. Don't worry about the numbers. You'll be given all this. You just need to know, in terms of the cycle, you know, the rules of using the cycle. If you can kind of get your hands on that cycle and really get the grips with it, you'll be absolutely fine. And this, you just rack up the marks. It's easy marks once you know how to use these cycles here. Okay, so this is a fixed cycle. You remember this cycle. Okay, remember this order: solid, aqueous ions, okay, gaseous ions at the bottom. Okay, so remember that structure there. Okay, so here's the numbers. So you'll be given these, like I say. So in this case, the enthalpy of solution, we're wanting to work out. We want to work out this bit, the enthalpy of solution. We want to work out the energy change here. So imagine this is like a roadblock. We want to go from here to here. That's what we want to work out, the enthalpy change of solution, because that's what it says at the top. So we want to work out that bit. So we imagine it's like a roadblock. We put a roadblock there. We can't go that way, so we need to go an alternative way. So we need to go here with the arrow, and then with the arrow here. You will be given the numbers. So the number here is +846. So that's just data that's given to you. And then we're then going to go with the arrow here. So that's -883. So we keep that the same. We put that into our calculator. So if you've got your calculator handy. So if you put that in, and you should get, hopefully if I've given you enough time to do that, so you should get -37 kilojoules per mole. Okay, so that's an exothermic process for this one. Okay, which is fine, because remember, if you're dissolving something, you want it to be exothermic. It's a favourable process, that. Because remember what we said, for something to dissolve or to be soluble, the energy here that's given out here when the solvent is attracted to ions must be the same as or greater than energy required to break this up here. Okay, if that energy released is greater than the energy needed to break that up, then overall you're going to get something that's exothermic. It's not massively exothermic, but nonetheless it still is. Yes, it is -37. That's it. Well done. Right. Okay. Spot on. Right. Okay. So, fine. That's all you need to know about enthalpy. Hess cycle. Not Hess cycle. Enthalpy change of solutions, hydrations, ionic compounds, lattices, and Born-Haber cycles. That's all that bit done. Okay. So that's that bit finished. So we're just going to move on towards the last sections. Well, I hope that's fine. So we're just going to move on to the last sections, which is entropy. Okay. Now, be prepared to get your mind blown with this, because this is, if you haven't heard of entropy before, you'll think this is the most bizarre thing you could have in chemistry, I think. But if you have seen it, you'll probably understand why. Okay, it's got some funny terminology. So, just before I move on to entropy, all this stuff we've been looking at is enthalpy. Okay, so enthalpy is to do with endothermic and exothermic reactions. So exothermic reactions are good reactions. Okay, so good reactions, they're favourable reactions in everyday life because the products are lower in energy than the reactants. That's an exothermic reaction. Endothermic reactions, you don't get many of them because the products are higher in energy than reactants, so that's not a favourable process. So that's enthalpy. Okay, I'm going to introduce you to a new type of energy, which is called entropy. Okay, don't mix the two up. Okay, so let's have a look. Entropy. Right, so entropy, get ready for this, is the measure of disorder in a system. Okay, so we're going to be using words like random, chaos, disorder. We're using words like this. It just sounds so unscientific, but these are the words that you use. It's about disorder. It is an actual word that you can use in the exam. So it's a measure of disorder in a system. So entropy is given the letter S. So enthalpy is H, entropy is S. And it's the number of ways that energy can be shared out between particles. Okay, so the more disorder there is, the higher the level of entropy. Okay, I've got another analogy. If you've seen any of my videos, you see I use analogies all the time because it tries to make it a little bit easier. So solids have the lowest level. Now, you would have seen this before. This is like stuff you would do maybe at the back end of primary school or start of secondary school. So solids, liquids and gases, that's how simple it's going to get. It does get a little bit more complicated than this, to be fair. So basically, solids have this regular arrangement, remember? Okay, nicely, neatly arranged, tightly packed together, nice and easy. Liquids, random arrangement, but still tightly packed, as you can see there. And gases are spaced out. There's loads of space there, much more random. They kind of float around as and when they can. Okay. Now, in terms of order, this kind of makes sense. Solid is more ordered. Okay. It has the lowest level of disorder. It's nicely ordered and organized and arranged. Whereas your gases are more disordered. They kind of just do what they want. It just looks like a right mess. Okay. Now, increase in disorder as we go across from solid, liquid to gas. And we also get an increase in entropy. Okay. We get an increase in entropy completely. Okay. So, the number of particles also affects entropy change. Number of particles also affects entropy change. So, if a reaction in the same state but more moles are produced, then entropy also increases. So there's more ways in which that energy can actually be distributed. Okay, so you can see going from a solid to a gas is an increase in entropy. So you're going more order. Okay, more disorder. Sorry, and also if let's say you had gases and you're producing more moles, if you're producing more moles, then you've got more ways in which then particles can arrange themselves, and therefore entropy increases there as well. So a classic example is this one here. So you can see here we've got 1 mole of N2O4, which is here, so your dinitrogen tetroxide, and then you've got 2 moles of nitrogen dioxide, so it's 2NO2, as you can see on there. Okay, so you can see here they've gone from 1 to 2 moles. This is an increase in entropy, despite them both being gases, so they both have this arrangement. We've got an increase in entropy. Okay, so just before we move on, the analogy I'm going to use is like a messy bedroom. Okay, nature has a tendency to move from an ordered space to disordered. Okay, if you think about your bedroom, I don't know how tidy you keep your room, but if you it's easier for it to get into a mess, i.e. dusty and stuff all over the place. It's easier to do that. It doesn't take much energy to do that, but to put it back and tidy it up and put it into some kind of order, that takes energy to do that. Okay, that's quite energy intensive. So same with particles. Okay, it's far easier. There's a tendency to move to more disorder. That's a favorable process. Okay, so anywhere where you've got an increase in entropy, that's a favorable process. So whether that's you're producing more moles or you're going from a solid towards a gas. Okay, there are two methods in which it's more favorable. Okay, right, I hope you've got that. That's entropy. That's what it means. So now what we're going to do is we're going to apply that concept to some specific examples, okay? So a reaction can be spontaneous or it can be feasible even if it's enthalpically unfavorable. So remember, something which is endothermic is not favorable, okay? They just don't happen because you're producing products which are higher in energy. But a reaction can still feasible at room temperature if it's entropically favorable. Okay, so we've got two parts here. So a reaction will tend towards more disorder. So remember what we said there. So it's going to tend to more towards a gas. Okay, so we get an increase in entropy. So increase in entropy, that's an energetically favorable process. Okay, and some reactions are enthalpically unfavorable, so they're endothermic. So normally that just would never go in a month of Sundays. It would definitely not go. But it can still be spontaneous if the entropy changes overcome the enthalpy changes. Okay, so you've got two things happening in a reaction. You've got an enthalpy change, is it exothermic or endothermic? And you've got an entropy change, is it going to something that's more disordered? So you've got two parts here. It's like a tug of war between the two. Okay, which one can override the other? And we'll look at Gibbs free in a minute as well. So let's have a look at this example. So a reaction between hydrated barium hydroxide and ammonium chloride shows how entropy changes overcome enthalpy changes. Okay, so we've got two solids are mixed and we get a gas, a liquid and a solid is produced. Now if you go to school, if you go to college, or if you've done this in the lab, this is a brilliant reaction. Okay, you literally take two solids and you can see them there. Okay, there's your two solids there. So you mix two solids in a beaker. Normally you'd have them in a beaker, you'd have a block of wood underneath, okay, and then you'd put a bit of water in between the wood and the base of the beaker, and you put the beaker on top of that wood with the water in between. And then what you do is you mix these two powders together and the temperature drops dramatically. It's a very endothermic reaction, and it freezes the water, and then you can effectively pick the beaker up and the block of wood is stuck underneath. It's really brilliant. Honestly, it's the most endothermic reaction I think you'll ever. You don't need to heat it up. Obviously, you don't need to heat it up or do anything like that. You literally just mix these two powders and it goes to a liquid. You form a liquid and you get this smell of ammonia coming from it as well. It's a really good reaction. So if you haven't done this, see if you can ask nicely. See if your teacher or lecturer will can do this reaction, or even have a look on YouTube. Have a look on there and you'll see this reaction is brilliant. Anyway, it's a severely endothermic reaction. Normally, endothermic reactions don't work. Okay, they just don't go. You would have known that from year one. Okay, year one chemistry. So, endothermic reaction is very endothermic. It's not favourable. Enthalpically, it's not favourable. It's plus 164. These reactions don't happen. Okay, but what we've got here is we've got 3 moles on the left-hand side. You can see there, we've got 1 and 2 there. That's 3 moles on the left. But we've got 13 moles on the right. That is entropically favourable. We're producing more moles than we had at the start. Entropically, that's good. Okay, it's a favourable process. And then obviously we're starting with 2 solids as well, nicely arranged, loads of order in there. And we're making a gas and a liquid and a solid. So we're making a gas and a liquid. These are more disordered. That's entropically favourable as well. So there's 2 things here that make it entropically favourable. And this explains why, even though this reaction is endothermic, this explains why it actually goes like that. Okay, there's no, literally just mix the powders together and it just goes. Okay, the reason why that works is because of entropy. Okay, so that it can only be explained using that method. Okay, so just still building on to entropy. Okay, so just looking at the calculation. So entropy, or the entropy change delta S, can be calculated between your reactants and products. I assume all that's fine. Nobody's put any comments on there yet. Okay. So the entropy change delta S, okay, is the products minus reactants. This is easy. This maths is dead easy. Okay, there's nothing to worry about here. Units of entropy, though, just a key thing. The thing you need to watch out for here is joules per Kelvin per mole. That's the thing you need to look out for. Okay, it's not kilojoules per mole, it's joules per Kelvin per mole. But this is really easy. Okay, you'll see. So entropy values are given as a standard value. You've got that little underground symbol. Okay, you've got a circle with a line through it there. Okay, there's your line there. So Standard conditions is 1 mole of substance, 100 kilopascals, 298 Kelvin. They're your standard conditions required. Okay. So let's look at an example. I'll show you how easy this is. Okay. Taking that reaction that we'd seen before. Okay. We need to work out the entropy change for this reaction. You will be given all of the data that you need. That makes it really easy. Okay. You just need to remember to make sure that you take into account the number of moles that you've got here as well. That's the only thing you need to do. So there's our entropy values there, okay? And we're going to put our numbers in. So we're going to work out our products first, okay? So our products are 2 lots of ammonia. So we should have 2 lots of 192. Sorry, I should let you work this out, shouldn't I? So 2 lots of 192 because ammonia is 192. You've got 10 lots of 70 and you've got 124. So that gives you an entropy value of 1208. So see if you can work out the enthalpy value for the reactants. So if you've got a calculator handy, see if you can work that out using this data here. I'll just give you a minute or so. We're nearly finished, by the way. This is a whole topic, though. It's quite a lot. There's quite a lot of information here, so it's giving you a kind of a good overview, really. Okay, so your products or your reactants should be 617 joules per Kelvin per mole. So that's what you should get there. Okay, and then basically all we do is we take that value and we subtract it away from that value. That's it, 617. That's it. So we take that value and that value. So remember, we are the numbers here is 427. That's your barium hydroxide. That's the value there. Okay, that's it. And then you've got 2 lots of 95. Okay, so if you put them numbers in, you literally subtract them away from each other, and you should get 591 joules per Kelvin per mole. Okay, so that's a positive value. Now, positive entropy values are good. Okay, that's a favourable process. Don't get that mixed up. It doesn't help really, but don't get that mixed up with enthalpy. A negative enthalpy value is exothermic. That's good. A positive enthalpy value is endothermic. That's not favourable. Okay, but a positive entropy value, that's entropy, positive entropy value is favourable. A negative entropy value is not favourable. Okay, really important. So anything that's positive means that it's entropically favourable. Doesn't mean the reaction will go, because you've got enthalpy as well, but we'll look at Gibbs free later for that. Okay? Right. Okay. So this is where we're going to look at something called Gibbs free energy, and this is the last bit, or the last sections really, of this live lesson. So we're going to be looking at something called Gibbs free energy. Okay. So all Gibbs free energy does is it tells us, it's really, really clever. This is like, if only this could tell us the lottery numbers. But basically, it tells us if a reaction is actually going to go or not. So this is a tool where we can actually put the numbers in. And before we even do the reaction, we can work out if it's actually going to work. If we calculate it, and it Gibbs free, or the delta G bit of Gibbs free, tells us that the reaction is not going to go, then it won't go. So this is really useful for chemists. This is really powerful because it means that we're not wasting our time mixing things together, and it won't work. It would never work anyway. So Gibbs free is a really good way of telling us before we actually do the practical, will it actually work? Will it actually react? Okay, this is just, it's really clever, this stuff. Okay, so this is what we call Gibbs free. Okay, so it's telling us if the reaction is feasible or not. Okay, so the reaction, or the equation you need to know, is delta G equals delta H minus T delta S. Wow. Okay, so you've got here delta G is Gibbs free, okay, equals delta H, that's your enthalpy change. We've seen that already. You've just seen that in year 1 chemistry. Minus, and T is temperature. Let me just bring that up there. There you go. That's your enthalpy change in joules per mole. T is temperature. That's in Kelvin. And delta S is your entropy change. We've just seen entropy before. So all we're doing is we're pulling enthalpy and entropy and we're putting them together in one equation. So we're trying to work out, which one's going to have the greatest effect on feasibility. Okay, so it's bringing both of them together. Really powerful equation. The units is joules per mole. Okay, so that's the value of delta G. The basic rule here is that a reaction is feasible in theory. okay, if delta G is negative or 0, okay? It must be negative or 0. If it's positive, what that's telling us is that in theory, this will not go, this reaction will not go. So that's the test. If it's negative or 0, then it means it will go, okay? In theory, it will go. We say in theory, okay, because we've got to be careful. We might not actually observe a reaction occurring. That seems a bit strange. So you can calculate it as it being feasible and say, yep, delta G comes out negative, so therefore this reaction will go. But it might be the case that the activation energy might be too high, or the rate of reaction may be really slow. So for example, a classic example is rust. Rust is obviously reaction. If you see a nail, an iron nail, it rusts. That's a feasible reaction because we see rust around us. It's a really slow reaction though. You wouldn't sit there and look at a nail because it's not going to rust in front of your eyes. It's going to take a while to do that, but it's still a feasible reaction. Okay, so just be wary of that. Okay, it's a classic exam question for them to ask and say, oh, this you've calculated as feasible. Suggest why it's suggest why you may observe nothing. And that might throw you and think, well, hang on, I calculated it as feasible. I must see something. That's the reason why you may not. It might be just such a really slow reaction. Okay. So let's have a look at an example. So we're going to calculate the free energy, so delta G, of the reaction between barium hydroxide and ammonium chloride. Okay. So that was the reaction that we'd seen before. Remember? Okay. So we need to know the following information from the previous slides. So we worked out our entropy change, remember, from the previous slide. So that was 591 joules per Kelvin per mole. That's a positive value, so that's good. Okay, that's a feasible in terms of entropy. The enthalpy value was plus 164 kilojoules per mole. That's not feasible. Okay, so anything endothermic wasn't a feasible reaction. So entropy was feasible, enthalpy it wasn't. Okay. So it's a case of which one is going to override the other, okay, and that's what Gibbs free. Are the units of Gibbs and enthalpy the same? Enthalpy is kilojoules per mole, okay, Gibbs is joules per mole, okay, very important, yeah. Okay, so let's put the numbers in. So delta G equals delta H minus T delta S, really straightforward. The key thing actually from what Trash said there is that you've got 164,000. Okay, 164,000 here. That's the enthalpy change. Normally, you're given enthalpy in kilojoules per mole. Okay, normally that's what you're giving it in. But you need to convert that into joules per mole. You need to multiply it by 1,000. Really, really important. Loads of people put this down and they don't convert that into joules per mole. Okay, and you get it wrong. You're out by 1,000. You must make sure that's joules per mole. That's the tricky bit. Okay, just remember that. Temperature 298 Kelvin. Delta S 591. So we put all that in our calculator. So if you've been on the ball, you might have grabbed your calculator with this, and you should have got a value of minus 12,118 joules per mole. This is negative. Delta G is negative. So remember, if delta G is negative, that means it's going to go, and definitely does. Okay. Again, look at this. If you have done this experiment, or if your teachers or lecturers showing it, or have a look online, you'll see it goes really, really quick. Okay. So no problems with that one. And delta G is telling us, Gibbs is telling us, yeah, this is feasible. Definitely, it's negative. Okay, at this temperature, at 298 Kelvin. Okay. Right. So let's let you get that one. Okay. So, just looking at Gibbs free, what we're going to do, the exam board. And this is tricky, this bit here. I must admit, this bit's really hard. I'm going to try and make it as easy as possible, okay? This is fine because they've given us data. We've got numbers here. The exam board can be a bit mean and not give you any numbers at all, and they want you to comment on whether the reaction's going to go or not, whether it's feasible or not, okay? This is quite mean. So this is where we're using a hypothetical scenario for these examples here, okay? So, temperature may have an effect on reaction feasibility. Okay, so we're looking at if we heat a reaction up, if we increase the temperature, that may make it more likely to go. If it's too cold, the reaction may not go. So you know that, for example, to get some reactions going, you have to heat it up. You have to heat it up, you have to give it some heat energy. Some reactions won't go at room temperature because it's just too cold. So what we're going to do here is basically we're going to try and work out if a reaction is feasible at a given temperature without any numbers, okay? Without any numbers as such. So we're going to look at different scenarios, okay, in this example, when delta H and delta S is changed and the delta G value. So we're going to use that equation we've seen before, and we're going to try and link it all up together, okay? So I'm just going to, yeah, okay. So let's look at the different scenarios. Now you can see here that we've got, let me just move myself around there, that should be fine. Okay, that should be fine. Okay, so what I've got here is a table, okay, and a table is showing us theory without any numbers. You see there's not a single number here, okay, so we've got an enthalpy value, delta H, which is negative, and we're basically giving you different scenarios. So if delta H is negative, delta S is positive, okay, then delta G is always negative, and is it feasible? Yes, at any temperature. So what we're going to do is we're going to go through each one of these, and we're going to, in theory, use words to try and explain if something is actually going to go, okay? Remember this rule though, if a reaction is feasible if delta G is negative or if it is 0, okay? So the best thing I would do here, in this case, is you take that equation and I would split that into two halves, okay? I find this a lot easier, okay? So delta G equals delta H minus T delta S. Just split that down the middle. See it as a bit like a seesaw, okay? Split it down the middle and you say, right, we have two halves to this equation. We've got a delta H part, which is this bit, and we have a T delta S part, and we've got a minus in front of them. So we've got this bit and this bit. Imagine it like two boxes. Okay, we're going to put some in the delta H and some in the T delta S. So we've got two halves to this. This makes it a lot easier to work out our thing. Otherwise, you just get lost. Otherwise, if you don't do it. So I'm going to explain it this way. So I hope it works anyway. Right, we're going to go through each one of these. We're going to start with the top one first. So look at the first row. Even if T, so temperature, was at its lowest, that's 0 Kelvin, that is the lowest it can go. You can't get negative Kelvin values, okay? So 0 was the lowest. Delta G would always be negative, okay? So exothermic reactions with a positive entropy would always be feasible at whatever temperature it is, okay? So you can see here, if we put the numbers in, let's have a look. Oh, actually, no, if we don't put the numbers in, I'll show you the numbers in a moment. Well, it's on the next slide. So you can see here, if whatever that value is, if this is negative and you're subtracting that by a positive value, then it's no matter what value this is going to be, that's always going to come out negative. So that means it is feasible at whatever temperature you put it in, okay? So they're the most feasible types of reactions, okay? They're the conditions. So if we look at the second row, that one there, okay? So look at the second row, even if T was at its lowest, that's 0 Kelvin, delta G would always be positive. So an endothermic reaction with a negative entropy would never ever be feasible, whatever the temperature. So these reactions will never go, okay? So there's no numbers here at all, yet we're commenting on whether a reaction will go or not, okay? So just imagine it. You've got a positive value here, okay, that's positive, and you're subtracting it by a negative value. So that's a minus and a minus, which is going to be a plus. So that's always going to be positive. It's never going to be negative. So that will never work. Okay? Right. So let's look at the third one. This is a really good one, I think. So the third row. So freezing water is actually an exothermic process. Okay? Delta H is negative. It releases a little bit of heat when we're forming water. We're going to a more ordered arrangement. Think about it. We're going from a liquid, which is random, and we're forcing it into an ordered arrangement, which is a solid. Entropically, that's not favourable because you need to put, you need to try and get it into that kind of arrangement. Okay. So a liquid to a solid, delta S is negative. Okay, that's entropically not favourable. Freezing only happens below a certain temperature. Do you see what I mean? So you can't freeze ice unless you get it below 0 degrees Celsius. If it's anything above that, then it won't freeze. So you've got an enthalpy value here, which is negative, an entropy value, which is negative. So delta G will be negative, but only at lower temperatures. Okay. So how do we work this out? So let's put some numbers in to use it as an example. So these are just generic numbers. It's nothing to do with the ice example here. So if delta H was minus 100,000 and delta S was minus 100 joules per mole, okay? So at 500 Kelvin, just put the numbers in. So minus 100,000 minus 500 times by minus 1,000 minus 100. So I'm just using these numbers here just as an example. It's got nothing to do with the ice, so I don't want you to be confused and thinking, well, that doesn't really make sense. So you can see at 500 Kelvin it's feasible, okay, because you get a delta G of minus 50,000. But let's say if we put in at higher temperature, same numbers, you see at a higher temperature delta G comes out as positive, so it's not feasible. So these reactions are more feasible the lower the temperature, okay, when you have this scenario here, okay. I hope you're following, okay. There's one more bit here. Okay, so the last row, which is this one here, so this is where delta H is positive and delta S is positive. So this is the fourth row. So a classic example is the decomposition of sodium hydrogen carbonate. It's an endothermic process. So that's an enthalpically not a favourable process, enthalpically, because it's endothermic. But we're going to a more random arrangement. We're literally going from a solid, that's your bicarb, when we heat that up, it's going to a gas. It's turning into these bubbles, okay? So this only happens above a certain temperature. We only get that conversion from solid to gas when we're above a certain temperature. We make crunchies, I love crunchies, or cinder toffee. So basically, you've got bicarbonate. When they bake this here, you get the little bubbles here. That's a little carbon dioxide gas that's been trapped in the middle there, okay? So put some numbers in. Let's have a look at it as an example. Same numbers as what I used before, just to show you. So we're doing it at 500 Kelvin. You can see here, we do 100,000. That's a positive value this time. So you've got a positive enthalpy value and a positive entropy value. I've just picked random numbers. It doesn't matter about the numbers, okay? So you can see it's not feasible at 500 Kelvin. But if you do exactly the same at a higher temperature, you can see, there we go, there's the temperature. That's the only difference there. Then it is feasible. So you can see this, in this scenario here, it will go, but it needs to be at a certain temperature. It needs to be at higher temperatures, okay? Right, last bit, okay? So, I hope you're following it so far. I hope so. You can go back, like they say, all this will be put onto Allery Chemistry YouTube channel. It'll all be on there. You can go back and look at it at your leisure. I think it takes YouTube ages to put it on. Best to check later on tonight or in the morning. So, the temperature at which a reaction becomes just feasible can be calculated. This is so useful for chemists because if we're doing a reaction and we need to know what temperature do we need to what temperature do we need to heat this to get this to go. What we don't want to do is, if the reaction only needs 50 degrees Celsius, we don't want to be ending up heating the reaction vessel to 100 degrees because we're just wasting energy. We don't need to heat it that high. We want to try and get away with the minimum amount of energy required to get this reaction to go, because it saves money. We're not wasting money on wasting fuel, and also a lot of the heat that's used to get reactions going uses fossil fuels, and so it's better for the environment. So chemists, if we can work out the minimum temperature we can get away with to get a reaction to go, then that's going to be really, really powerful to us. So this is how we're going to work it out, okay? So a reaction is just feasible when delta G is 0, okay? So that's when it's just about feasible. That's the tipping point, the critical point. So we can rearrange the equation to work out the temperature when delta G is 0. That's the point at which it just becomes feasible. In other words, that's the point we want to try and hit, okay? So what we can do is we can take the delta G bit out because we assume that's got a value of 0, and we get this equation that's left. So T equals delta H over delta S. Okay, so notice the delta G is being omitted because that's equals 0. So what we're going to do as an example, like say it's the last bit, okay, and we've literally gone through the whole topic, which is brilliant. So calculate the minimum temperature required for sodium hydrogen carbonate to decompose, okay? So we've got sodium hydrogen carbonate, that decomposes into sodium carbonate, water and carbon dioxide. We can see it's an endothermic process. Delta H is 129 kilojoules per mole. Okay, so this is the reaction here. So we need to work out the minimum temperature, okay, required for this reaction to go. We want to try and get with the lowest energy required. So there's our values there. There's entropy. Okay, so we're going to calculate delta S first. So remember, products minus reactants. So entropy of products is 539. So our products are sodium carbonate, water and carbon dioxide, and our entropy of reactants, 2 lots of 102 because that's the value there. That's 2 lots of sodium hydrogen carbonate. That's 204. We do products minus reactants. That gets us a delta S value of 335 joules per Kelvin per mole. Okay. Right. Okay. Happy with that so far? So we've just worked out delta S there first. This type of stuff they will do in the exam as well. They'll ask you to work out the minimum energy. I think if you do salters, you don't need to know this, okay? But all the other exam boards, you are expected to be able to do this, okay? Right, so then we assume that delta G equals 0, okay? So T equals delta H over delta S, okay? That's the equation that we've got there. So we just put the numbers in. So the minimum temperature, that's what we want to work out, the temperature, is 129,000, okay? That's delta H. That's what we've got there. Remember, we need to convert that from kilojoules per mole to joules per mole. So that's why we need to convert that to multiply that by 1,000. Delta S we've just worked out here is 335. We divide them two numbers together and we get the minimum temperature that we need. So if you put them numbers in, and we should get 385 Kelvin. Okay, so that's the minimum temperature required for this reaction to occur. Okay, right, that's it. Okay, that's everything you need to know. There's a lot there. There's a lot of maths there. Like I say, it's important that you're able to practice this. If you get your hands on this and you can understand, particularly Born-Haber cycles, and entropy always comes up. It's just always going to come up in your exam, okay? And Gibbs free, it's on all exam boards apart from salters. If you do salters, you don't need to know about Gibbs free. Lucky you. But all the other exam boards, you do need to know about Gibbs free. Make sure that you can do this. Make sure you can work out the entropy changes, and make sure you can sort everything out there. Like I say, this is the video. This will go on to Allery Chemistry, onto my YouTube channel. Go through it again. Have a look through it. See if you can work through it. The questions I've made the questions this morning, so they're all on. There's a link on the description box for this video and also the scheduled video on Thursday. So click on that, get your questions done, and then we'll go through them questions and see how much you've learned from this video. Okay. Brilliant. Yeah, that was a lot there. Normally that would take, just to give you an idea, in school or college, that might take 3 or 4 lessons to do. So really crammed a lot into one go. Okay, so have a go at the questions, see how you're doing with it, and then hopefully you should be fine. If you haven't already subscribed, please subscribe to the channel. That'd be brilliant. Everything on there is free, and it will always be free as well. All I just need you to do is hit the subscribe button, although no doubt a lot of you probably are already subscribed anyway. Okay, we do this for all topics, or is it only for lockdown? Yeah. Just while the lockdown is on, I am actually furloughed from work. So if I get called back to work, I get a week's notice. So if I get called back to work, then I won't be able to do it. So it's just to kind of keep me occupied, I suppose, and help you lot out, because it can't be easy if you're not at school or college. It can be a bit difficult, I think, trying to learn this, particularly if you've got A levels. Obviously not this summer, but next summer. I think it just keeps your mind ticking over, so you don't forget anything. So it's the reason why I'm doing it, really. So yes, I'll do it for as long as I can, physically do it. Brilliant. I hope that was helpful. I think looking by the responses, I think some people have obviously found it helpful, which is good. There's a lot of information in there, but have a practice, and we'll have it. We'll go through that on Thursday, same time, in the same place. All right. Brilliant. All right. Thank you very much for your time. That's no problem. That's no problem. It's all the stuff on there. Actually, just before I go, there is more stuff going on there. Year 2 videos are going on. They're on for OCR-A. They're on for EdXL, if you do EdXL. The AQA ones are nearly finished. I think there's about 4 more videos scheduled to go on there. And if you're doing salters, they're going on. They're going on starting next week. They should start and go on as well. All the year 2 videos for the 4 main exam boards will all be on by the end of the month. It's all for free, so go and have a look on there. And these ones are them ones on the channel are all tailored to an exam board. This one I've tried to kind of keep generic as much as I can. Okay. Brilliant. All right. Right. I'll see you on Thursday if you can make it. That'll be absolutely fantastic. The questions are all on there on the link. Click on it. Have a go at it. Don't worry if you don't. If you're not, if you get a bit stuck, you're not sure. I'll go through the answers, and it's just trying to make sure you can do it. All right. Brilliant. Right. I'm going to shut up now because I'm just ranting. All right. Okay. Right. Thanks very much. See you later. Bye.